Hello everybody, let's continue our discussion on Kepler's 3 laws of planetary motion. We've done laws 1 and 2, and it is now time to talk about Kepler's 3rd law of planetary motion. Arguably the most important one, because it is the one that unlocks the scale of the solar system. It allows us, if we can measure a planet's orbital period, something that is observable, we can then calculate how far away it is from the sun on average, which remember that is the semi-major axis distance of a planet. So on average, how far away is a planet from the sun? That's the semi-major axis distance. For Earth, that number is 1 astronomical unit, 1 AU. So what I'm going to do in this video is I'm going to walk you through Kepler's 3rd law. I'm going to help you learn how to solve it, because yes, you have to do a little bit of algebra with this one. And then I'm going to work some examples and tell you a little bit of the limitations, which will set the stage for moving beyond these empirical laws that Kepler came up with. So Kepler's 3rd law of planetary motion. It's stated as the square of a planet's orbital period measured in years, and yes, it must be in the unit of years, is equal to the cube of its semi-major axis. And that semi-major axis must be measured in astronomical units. So this one is sort of a unit-locked equation. You can only use it if you're going to use your orbital period, indicated by P here for period, must be in years. And your semi-major axis, how far away on average a planet is from the sun, or any other object in orbit around the sun, must be in astronomical units. So writing out that the phrase of Kepler's 3rd law, the sentence of Kepler's 3rd law, into an equation. And what are equations other than a very succinct way to write complex ideas? You get that the period squared equals the semi-major axis cubed, or simply P squared equals A cubed. Now you might have to write this down 10 times, 20 times, 30 times, however many times you need to. Just remember that it's P squared equals A cubed. The most common mistake I see is people reverse the squares in the cubes. So write it down until you got P squared equals A cubed. Come up with a mnemonic, however you can learn it. Just make sure you know that one, because you will have to solve this equation. The way that you'll work with this equation in this class is that I will give you the orbital period, and then you'll have to tell me the semi-major axis, or I'll give you the semi-major axis, and you'll have to tell me the orbital period. Let's look at the easier of the two scenarios where I tell you the semi-major axis distance. I give you the A part of P squared equals A cubed. So I'm just going to walk you through this just in case you need to dust off a little bit of how you unsquare squares and how you solve equations. So let's say I give you the semi-major axis and you have to tell me the orbital period. So given A, solve for P. P squared equals A cubed. So how do you get rid of a square? Well, you take the square root. And if you take the square root on one side, you got to take the square root on the other side to keep everything equal. That's what the equal sign is telling us. So I take the square root of P squared, I take the square root of A cubed. And that just gives me P. That's what I'm looking for. I've solved for P, and it equals the square root of A cubed. Now, sometimes you might have trouble looking for the square root sign, or even worse, the cubed root sign if you have to do that one on your calculator. And maybe you just like to work with powers, exponents. And this is just a reminder that what I could do, instead of taking the square root, it's the same as raising something to the 1/2 power. So I could raise both sides to the 1/2 power to get that P squared raised to the 1/2 power is just P, the period, equals A cubed raised to the 1/2 power, which is A raised to the 3 divided by 2 power. A to the 3/2. Remember with exponents, if you have A cubed raised to the 1/2, you'd take 3 times 1/2 to get the new exponent. So those are equivalent. Those two are equivalent. You're probably for this one going to use the P equals the square root of A cubed. The harder direction is I will give you the period and you have to tell me the semi-major axis. This is the more practical one because people can observe the periods of the planets. So P squared equals A cubed. Again, since this is an equal sign, it doesn't matter what side, which one is on, I can go ahead and reverse the entire equation, and I can get, that's the same thing as A cubed equals P squared. And that's just because I like to work with the variable I'm solving for over on the left. That's how normally done. If you don't like it, you can just do it however you like. But I like my a on the left, so let's use a cubed equals p squared. How do you get rid of a cube? Well, you take the cube root. So you uncube a cube by the cube root. So I can get the cube root of a cubed, and if I do it on this side, I have to do it on that side, and I get the cubed root of p squared. So the cubed root of a cubed is just a. Hey, I've solved for the semi-major axis. I'm at my goal already, and it equals the cubed root of p squared. So if I gave you the period, say 5 years, you'd put 5 here, square it, 25, and you take the cube root of 25. Done. Or we can use, and now you'll see why most people don't know where the cube root button is on their calculator. So this is where it's a little easier to work with the power notation, the exponent notation. So a cube root is the same thing as raising something to the 1/3 power. So a cubed raised to the 1/3 power. Multiply 3 by 1/3, get 1, get a. And then p squared raised to the 1/3 power. I take 2 times 1/3 to get 2/3, and I get a equals p raised to the 2 divided by 3. Or you could go ahead and square p. Again, if it's 5, you get 25 and raise 25 to the 1/3 power. However you like it, go through the examples, practice with your calculator, look at the examples where I have answers until you can consistently get the right answer over and over. Whatever method makes the most sense to you, pick that one, stick with it, and grind it into your memory. And this is just there, just to give you a quick little aside, just to let you maybe bring this home, because I've noticed over the years that p squared equals a cubed, people get a little confused, and I think it's because it's not how we normally see variables. It's not how we learned our algebra. We always learned algebra with y's and x's. So I just want to go ahead and let you know that you can replace the p with a y and the a with an x. So you can go back to what you're used to, because I bet if I gave you y squared equals x cubed, and I told you that x equals 3, you could then solve for y. Sure, you might have to shake off some cobwebs, but that is probably one of those things that you learned how to do, and you got pretty good at it. So y squared equals x cubed, and I say x equals 3. Can you solve for y? And what you do is you probably say y squared equals 3, what's what x is, cubed, and then you go, oh, 3 cubed is 3 times 3 times 3. So y squared equals 27, and then you take the square root and solve it. And this, just replace y with p and x with a, and boom, you're done. Make sure that you get your units right, that p is for period in years, a is for semi-major axis, and AU. So why is all of this so profound? We can go out there, and if you're dedicated and have a lot of time on your hands, and a little bit more know-how than we've covered so far in the class, but nothing like really, really hard, like deeply hard to understand, you could go out there and do observations of the planets, like look at the Tycho Brahe data, things like that, and you could observe what the orbital period, how long it takes a planet to go around the sun one time. You could go ahead and observe that. So P is something that we can get, and you don't need any special equipment. It's been known for a long time for the planets. We've known what P is, the period, the orbital periods are. Once you know the orbital period of something, you can then use it to solve for how far away it is from the sun. So when Kepler first did this, he knew the orbital periods, and then he calculated the semi-major axis, how far away on average all the known planets were from the sun. And for the first time, out there, written out in front of him, he had the scale of the solar system. Sure, he only knew things and how many times farther away they are from the sun than the Earth is. Like Jupiter at 5.2 AU is 5.2 times farther away from the sun than Jupiter. But that is still profound. That is a real distance, something that we can picture in our heads. And everybody, Kepler included, was blown away because all of a sudden, their universe, which was really just the solar system at this time, because they didn't know anything back out beyond it, all of a sudden, the solar system was much, 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 much larger than they ever expected. Their universe in size, the scale of where we all live in, exploded at this point in history, and we actually had a good scale on it. Pretty awesome, amazing, profound stuff going on there. So that's why I'm going to take the time and I'm going to ask you to learn how to solve this. Give me just 1 second because I want to run through some examples, which means I am going to work on a whiteboard. So let me go ahead and run through some examples. If you need to take a break, this is a great time to pause the video and go ahead and stretch it out. Let all the information seep in, because I know this is going to be a long video, but you deserve to see some examples that are beyond what's in the slides. You deserve seeing me work through the examples so you can follow along. So take a break, come back with pen and paper or pencil and paper or however you like to take notes. And by the time you get back, we'll be ready, and I'm going to go through 4 examples that are different than the ones that you have in the unit slides. All right, so hopefully you're going to not be paying attention as I fumble through making sure I can display my iPad. Share. Screen mirror. All right, so welcome back. I am going to run through 4 examples of working with Kepler's third law. And I'm going to work through them step by step. You'll probably want a calculator or open up a browser with a calculator so you can follow along with the calculations and watch these as many times as you want. I'm only going to do 4. I encourage you, I put some practice problems on Canvas for you to go through. Make sure that you go through all of those to really make sure you get how to do this. Yes, there will be questions on the first exam. There will be one where I will give you the semi-major axis and you have to tell me the period. There'll be one where I give you the period and you have to tell me the semi-major axis. I want to make sure that you can work with this equation in both directions. So without further ado, let me go ahead and jump in here and start the first example. You'll typically see these in words, but the first thing you want to do in a word question, pull out the relevant information. So I'm just going to work with the relevant information. And you read something like, okay, there's some object out in there. There's solar system, some comet. It has a semi-major axis of 20 astronomical units. What is the orbital period of that comet? Okay, so it has a semi-major axis of 20 AU. A equals 20 astronomical units. Now I know I'm working with Kepler's third law, so the first thing I'm going to do is write Kepler's third law, p squared equals a cubed, where I know p is in years, a is going to be in AU, and I know that a equals 20. Oh, let's just work with that then. I could go p squared equals 20, I just substituted that in, raised to the third power. What's 20 times 20 times 20? Well, 2 cubed is 8, 10 cubed is 1,000, 8,000. You might want to go ahead and use a calculator for that one. So now I have p squared equals 8,000. How do I get rid of the square? Well, I take the square root. So I get p equals the square root of 8,000. Now I'm going to pull out my calculator. So go ahead and do this as well. I'm going to take the square root of 8,000 and I get 89, and I'm only going to go to the first decimal point here. 0.4, I'm solving for a period, a time. So I'll make sure I put my unit years. Box in the answer because I'm proud of it. There we go. Not so bad. Let's work another example just to be sure though. So in example number 2. So now let's work with the planet Mercury. The planet Mercury has an average distance away from the sun of 0.4 AU. So it's 0.4 times the distance that the Earth is away from the sun. That's saying it's 2.5 times closer if you want to go ahead and work out the math of that. But we're just going to figure out what the orbital period of Mercury is if I know that a semi-major axis, A, equals 0.4 astronomical units, AU. So write Kepler's third law, p squared equals a cubed, I know what A is, so let's go ahead and use that information. P squared equals 0.4 cubed. Go ahead and work that out if you need to using a calculator. I know that 4 cubed is 64, and 1/10 is 1/1000. 1/10 cubed is 1/1000th. That would be 0.084. Did I get that right? Or 0.64? Yes, 0.064. You could use your calculator for that one. And now I have to take the square root of both sides to get that P equals the square root of 0.064. Gonna put that one in my calculator. 0.064, take the square root of it. And what am I gonna get? I'm gonna put this out to 2 decimal places, 0.25. 25 what? Oh, I'm solving for a period. Years. Box in your answer because you're proud of your work, and not so bad. Okay, so 2 examples down, and in those 2, I gave you the semi-major axis and you solve for the period. For this next example, let's work the other direction. So in this case, let's imagine that we discovered some object out there in the solar system, and astronomers are able to determine that it has a period. So this is our third example, of 100 years. Or maybe you're just curious, how far away would something from the sun need to be before it would have, or where it would have a period of 100 years? So we got to work with Kepler's third law. P squared equals A cubed. Remember, that's the same as A cubed equals P squared. So I like to have my what I'm solving for over on the left. So I'll have A cubed equals P squared. Well, what's my P? Is 100 equals 100 squared. What's 100 squared? 10 squared squared is 10 to the 4th, 10,000. So I have A cubed equals, just to clean this up a little bit, 10,000. How do you get rid of a cube root? How do you get rid of a cube? You take the cube root, which is the same as raising it to the 1/3 power. Raise it to the 1/3 power. So I have A equals 10,000 raised to the 1/3. I'm going to plug that into my calculator. 10,000, raise that, which is usually a caret sign, something that looks like that on your calculator. So on your calculator, you're probably going to put something that looks like this. Oh, let me write that a little more clearly. So that's what it looked like on your calculator. I don't want to confuse people too much, so I'm going to go ahead and erase that to the 1 divided by 3. So you can see that line right there, 10,000 raised to the 1 divided by 3. I put the 1 divided by 3 in parentheses, so it knows to actually raise it to the 1/3 power. And it gives me 21.5. 21.5 what? Well, I have semi-major axis, that's the distance, astronomical units. Proud of my answer. So any object in the solar system with a semi-major axis of 21.5 astronomical units will have an orbital period of 100 years, 1 century. Okay, so let's work one last example. In this one, let's do something that has an orbital period less than a year. So our orbital period in years will be 3/4 of a year. 0.75 years. Now, I'm going to go ahead and I'm going to give myself a reality check. The orbital period is less than a year, and I know that p squared equals a cubed. So if p is less than 1, is between 0 and 1, then a will be between 0 and 1. If Earth's orbital period is 1 year, and this object has an orbital period less than that, I know it has to have a semi-major axis less than Earth's. So my answer better be a number between 0 and 1. This thing cannot be farther away from the sun than the Earth is, on average. Okay, so if I get an answer where A is greater than 1, I know I've made a mistake. All right, so let's write it out. A cubed equals, what was P? 0.75. Square that. So that is going to equal 0.5625. I've already calculated that one out. You might want to use your calculator. How do you get rid of a cube? So we'd have a cubed would equal 0.5625. Raise that to the 1/3 power. Oops. Well, let's just go ahead and leave that there. We can clearly see what I'm doing, raising each side to the 1/3 power. So A is going to equal a cubed raised to the 1/3 power. Just gives me A. So I need to take 0.05625, raise that to the 1 divided by 3. So you can see what that looks like on my calculator. And I see I have a mistake. Put an extra 0.5625. Sorry about that. Always good to look at your calculator before you hit the enter. So 0.5625. Raise that to the 1/3 power. Gives me 0.8, oops, can't write today, 0.83 watt astronomical units. Circle it in. So I'm proud of that answer. So something that has an orbital period of 3/4 of a year, 0.75 years, has a semi-major axis of 0.83 AU, 83% the distance away from the sun that the Earth is. Okay, so now that I've worked through some examples, you can re-watch all of those. I do want to end this video with one final quick lesson. So I'm going to go ahead and stop sharing right here and bring my slides back up, because I want to tell you that while Kepler's 3 laws of planetary motion, especially Kepler's 3rd law, is really, 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 really great, they are tragically flawed. So Kepler's 3 laws of planetary motion, while absolutely phenomenal and absolutely revolutionized our view of the universe that we live in, were limited because they were just mathematical solutions to the data set that Tycho Brahe had. They didn't actually tell us how the planets were moving. They gave us answers about the orbital period and the semi-major axis, but didn't tell us what is making the planets actually do the moving. And without that meaning, without that bit of science behind it, means that Kepler's 3 laws of planetary motion only work for where they were derived from, which is the solar system. So Kepler's 3 laws of planetary motion only work for objects orbiting the sun. You can't use Kepler's 3rd law as it's written here, just p squared equals a cubed, where p is in years and a is in AU. You cannot use that to figure out the orbital period of the moon around the Earth, because the moon orbits the Earth, not the sun. You can't use it to solve the orbital period of the moons of Jupiter, the Galilean moons of Jupiter orbiting Jupiter. You can't use it for planets in orbit around other stars that are not sun-like. So this only works for objects that are in orbit around the sun. But we really want to understand how things just move in general. We want something that applies not just for our solar system and not just for things in orbit around our sun. We want something that works for orbits the universe round. Doesn't matter where you are or what you're talking about orbiting, what else. We need a little bit more physics. And for this, we're going to have to step into the world of Galileo Galilei and look at the foundation of modern experimental physics or experimental science. And then we're going to have to go look at the ideas of Isaac Newton, who came up with our first, or humanity's first concept of how things move, and a first concept of what gravity is, why we're stuck to the surface of the earth, why we're always pulled towards the center of the earth, why the planets orbit the sun. All of that is due to gravity, and Newton is the first one that gives us an idea of gravity. So that's what's coming up in the next two videos. Go ahead and tune in. I know this was a long one. Hopefully going through those examples is useful to you. Please check out the practice problems I have on Canvas. Also, check out the other examples I have on the unit slides.